Alright, positron decay. So here you would have to know how to represent a positron. Now what happens, sort of, is you have a proton. It emits a positron, or I like to think of it as it emits the positive part and becomes a neutron. So this increases the number of neutrons. And therefore, you lose one proton and gain one neutron. So for example, if you have boron 8, it has 5 protons, but if it emits a positron, then 4 plus 1 is 5, and 8 plus 0 is 8. So you go to the periodic table and you look up 4, and you see that it's beryllium. Alright, so let's do another example. Let's do boron 11. Boron 11, and the atomic number is 5, emitting a positron. The positive is not necessary in front of that one. So we see what's produced. So we need a 4, an 11, and the 4 is still beryllium. But notice we're dealing with different isotopes of boron and beryllium. Up here we had beryllium 8 and boron 8. Down here we have boron 11 and beryllium 11. Beta decay. And you can call it ejection of an electron. So here are the symbols. Here what happens is now a neutron. If you want to think about it this way, you can think of a neutron as made up of some positive part and some negative part that together are neutral. If you lose the negative part, alright, so this is sort of an in-between picture. This green is losing the negative part. You're going to be left with the positive part, which is a proton. So it's sort of like a neutron is changing into a proton. And these nuclear reactions are just a lot different than what we think about. Alright, so for example, tritium, hydrogen 3, ejecting a beta particle. We have a 0 and a negative 1. Now this negative makes it tricky, and your mind will like to play tricks on you. So it needs to add up to be 1 on both sides. So we need a 2 so that when we combine it with the negative 1, we get 1. So 2 minus 1 is 1. 3 plus 0 is 3. So this produces a helium-3 isotope. So, for example, carbon-14 emitting a beta particle. We get the atomic number from the periodic table. It's carbon. It's got 6 protons. So the bottom number will be 7. 7 minus 1 is 6. And then we need 14 plus 0 is 14. And then we go look up what 7 is on the periodic table. And it's nitrogen. And that's how you would do those. Now, this last type of decay is a little different. It's an electron capture. So this is a real electron. So you have your nucleus and your orbitals around, and you have electrons in them. Then an electron is actually being captured by the nucleus. Alright, so how is this happening? Well, you have your proton and you have your electron, and the electron is being captured sort of by the proton. So we have our negative and positive coming together, and when you get those together you get neutral, which is your neutron. So you lost a proton and gained a neutron. So here, this is the only one where you put those particles in the reactants. Now, I did talk about neutrons in a previous lecture. Those are involved in lots of reactions. They can be reactants or products as necessary, and the question would have to help you out by describing what was going on. But here we're talking about electron capture. So this is where the electron is a reactant. So if beryllium-7 captures an electron, it still has to add up the same on both sides. So 7 plus 0 is 7. 4 minus 1 is 3. So we go to the periodic table and look up number 3, and that's lithium. Our example here is argon-37. So argon-37, the atomic number is 18. If it undergoes electron capture, what will we get? 37 plus 0 is 37. 18 minus 1 is 17. So we get chlorine 37.